Okay, thank you very much. First of all, I would like to thank the organizer for inviting me to present my work in such a nice meeting. And I've done this work in collaboration with Juan Pedro Garhan, Federico Carolo, and Igor Lesanovsky. All of them are in Nottingham. And, well, the idea of this talk is the connection of ideas and methods between problems in classical and quantum non-equilibrium system in order to unveil properties of transport in boundary-driven one-dimensional system. The sketch of the talk would be, first of all, a recap about exclusion processes, known results, last deviations, and macroscopic fluctuation theory. Second, I will be explaining boundary-driven open quantum chains and how we can apply this classical methodology in order to unveil a fluctuating hydrodynamics and study current fluctuations and see how these current fluctuations imply hyperuniformity phases. Then at the end, I will be talking about the joint current activity fluctuations. Okay, this is a work in progress, but yeah, I will give you some insights into it. Okay, so very generally, exclusion processes are models which are paradigmatic in order to study non-equilibrium transport in classical systems. Exclusion means that particles can hop into neighboring sites provided they are empty. The symmetric simple exclusion process has a hydrodynamic limit, which is given by the diffusion equation with a d, which is constant. The diffusivity is constant. And at the reservoir, we can attach boundary reservoirs that extract or inject particles in order to drive it out of equilibrium. All right, we can consider also the ring geometry, the periodic case, in which particles jump on a ring, and we will see that if we apply a field into this system, we drive it out of equilibrium, and funny things happen at the regime of current fluctuations. Okay, this model presents a typical dynamics that is diffusive. That means that the dynamical exponent set is equal to 2. What we're interested in is to study its atypical dynamics, in the sense that what happens if we condition the system to have a certain value of an observable which is not typical. That observable can be the activity or the current in our case. So to study this atypical dynamics, what we have to use is the theory of dynamical last deviations. And this is done through the formalism of thermodynamic of trajectories. The simple exclusion process, microscopically, is described by the master equation, which is written here, with this ket of probability describing the probabilities of the system at time t, and it evolves with the generator given here, where W, C to C prime are the rates to go from configuration C to C prime, and RC are the escape rate. This is microscopically, but we are interested in time-integrated observable along a trajectory in time. As I have said, this time-integrated observable can be the number of jumps, which define the activity, or the difference of the number of jumps to the right and the number of jumps to the left, which would be the time-integrated current. In order to calculate the probability of the fluctuations of these observables, we have to perform this summation over the probability restricted to those trajectories that gives rise to the rare event that I want to observe. And this, as has been repeated in the previous talks, follows a last deviation principle where phi is the last deviation function. An analogous description is given by the moment generating function, which is taking the Laplace transform of this probability. And in this case, it follows as well a last deviation principle with extensive parameter t and a large deviation function, theta of s, which is the scale cumulant generating function. As its derivative, as we have heard in the first talk of this morning, give us the cumulants when we evaluate it at s equal to 0. So here we have the analogy between dynamical fluctuations and equilibrium, because we can see that T plays what in equilibrium plays the role of the volume, and K, our observable of interest, plays the role of the order parameter, while S is the conjugate field. In this case, the large deviation principle, the large deviation principle of P gives me the large deviation function, which would be the entropy, and its Legendre transform would be theta of S, that in equilibrium would correspond to the free energy. All right, so how can we extract these large deviations that are the analog of the free energy in non-equilibrium situations? Okay, we could perform from the microscopic dynamics, we could bias this generator, and by getting the largest eigenvalue, we would have this theta of s. But as soon as we go to larger system sizes, this becomes more and more difficult, and one would desire to have a hydrodynamic approach of this, a continuous approach of this problem. In that sense, the macroscopic fluctuation theory developed in the last 20 years makes possible the computation of dynamical large deviations in a rather straightforward way. Its result can be described from these fluctuating hydrodynamic equations that describe the evolution of the fluctuating fields in a system with a locally conserved observable that is constrained in this field rho. So we see here that the evolution of the density at time t is given by the diffusivity times the second derivative in space of rho minus the derivative of a noise. This noise is considered to be a white noise with average 0 and with a variance that is proportional to the mobility and is inversely proportional to the system size. So being we are in the regime of weak noise. And the transport coefficients sigma and d are related via the Einstein relation, where that says that sigma is equal to 2 times d times the compressibility. That can be measured by measuring the fluctuations of the density in equilibrium. All right? So the main result of the macroscopic fluctuation theory is that the joint probability of a trajectory given by the field rho and j is an exponential, follows a large deviation principle where the large deviation function phi is this quadratic functional, right? So from this probability, we can calculate any probability of any observable that depends on these two, okay? As for instance, time-integrated currents. And that is what we are interested in. To give you an insight of previous examples, in 2013, I, in collaboration with Pablo Hurtado, measured the large deviation principle of a weakly asymmetric exclusion process. That is, this simple exclusion process in which we apply a field enhancing the probability of jumping to the right with respect to the left. In this case, we measure the large deviation function, and we observe that above a critical current, we observe a flat profile. We see here that this flat profile is a trajectory in which is sustaining a j above a critical j. We see that there is no structure. However, as soon as we condition the system to have a low current, right, the system develops a traveling wave. And this is what we observe here. This is a space, all right, and this is time. And this is obtained with the cloning algorithm, all right, by following the trajectory of a clone. So this is very illustrative because we can see here perfectly how the system develops this traveling wave in order to minimize this this current. So in order to make it below the critical value. Here are the profiles of this associated to each current fluctuation as a function of the conjugate field lambda. All right. So we see that above a critical current, we have here flat profiles. Below, it becomes a traveling wave. Okay. And again, above another critical threshold, we have that the profile is flat. And this can be observed in the last deviation function that we have here, where above the critical current, the last deviation is quadratic, while below is not quadratic anymore. It means that its derivative, which we plot here, above the critical current is linear, and below is nonlinear. And this is the first derivative of the scale cumulant generating function. And we see that it goes from linear to nonlinear, so that the second derivative would have a jump, meaning that this dynamical phase transition is of second order, right? So here we have the lambda, and here we have the first derivative of the scale cumulant generating function, and we can see how it develops a second order phase transition as soon as we condition the system to have very low currents, all right? But what happens, for instance, when we condition the system to have large currents? In 2015, Rob Jack, that is here in the audience, Thompson and Peter Solich proposed this dynamical phase diagram in the symmetric exclusion process without a field in the normal SEP. And this is a bias on the activity S, and here we have a bias on the current given by H. And they determine that below this curve there is a phase-separated regime, while above we have a hyperuniform regime. Okay, I stress that this is in a closed regime because we will get, at the end of the talk, similar results, but in the open geometry. Okay, and we will specify what these hyperuniform states are. All right, and this was also determined by Lecomte, Garrahan, and Van Friedland in 2012. And a similar dynamical phase diagram has also been obtained by Karevsky and Schutz using conformal field theory. All right. Okay, but we want to use these ideas in order to unveil something in boundary-driven quantum chains, open quantum chains, right? And say analog, a paradigmatic model of open quantum system is the tight binding model, as we have seen in the previous talk. And this tight binding model is given, it's Hamiltonian, is given in this form. With J is the coherent hopping rate between sites, and A dagger A are the creation and annihilation operators, respectively. All right, this Hamiltonian describes either bosons, or both bosons and fermion dynamics. And if the system is weakly coupled to the environment, it can have a Markov description, and we can describe the evolution of the observable in the Heisenberg picture through this equation, which is called the Lindblad equation, right? Where here we have the coherent evolution, and the star is given, is telling us how the dissipation acts on the system. Okay, and it depends on this form through the injection and extraction rate at the boundaries. All right. Well, it corresponds to the action of the environment of the system when this system is weakly coupled to it. Okay. I'm coupling to this kind of reservoir with incoherent pumping at the edges. All right, that's my model. Then I'm going to consider as well dephasing, which is a key ingredient, and dissipation, right? In this case, as soon as we are dephasing, we will see that we will have a diffusive behavior. But as soon as we consider dephasing and dissipation, we have to add another dissipative terms in this Lindblad equation that are written here with nk equal to a dagger at site k times a at site k. And the question is, can we have a fluctuating hydrodynamic or MFT description in these systems when we take the diffusive limit? That's what we are interested in. And can large deviations describe the non-equilibrium stationary state dynamics? Yeah, that's like classical dissipation, put by hand in the system to see the effect on the hydrodynamic description. This is incoherent hoping, that is the analogous of a SEP, but here is written in terms of the Lindblad equation. But it would be like in this is classical dissipation, say. Then this is the dephasing term that is responsible of the loss of the coherencies in the system, all right? The point is that I want to study in the hydrodynamic limit the competition between all these quantum contributions, right? The dephasing, the dissipation, and the coherent hopping, and the effect of the boundaries, right? So the thing is that if I take the hydrodynamic limit here, I get the when I average in the occupation number, I have this evolution equation, right? With two contributions. A coherent one, which is given by this formula, and a dissipative one, which is classical like, all right? And if I take the hydrodynamic limit of this, I get a diffusion equation in which the diffusivity takes into account all the ingredients of the system. And I can see here that, okay, if classical hopping wouldn't be present, this is this phi, as soon as the dephasing is present, the diffusivity would be non-zero, so the system would continue to be diffusive. But I take this scaling in the coordinates of m is the site, t is the microscopic time, and I take this limit and I average, all right, in this way, the mean number, the particle mean number at each site, and that gives me this the field rho. Yeah, we get this second derivative. What we do is a local equilibrium approximation, right? Okay. But this is the hydrodynamics. What about the fluctuating hydrodynamics? In order to obtain the fluctuating hydrodynamics, I have to study the trajectories of the quantum system, right? Yeah, this I introduce it by hand. This is, by hand mathematically, all right? Okay, normally you don't study the effect of this. You just have dephasing and coherent hopping. But I impose mathematically in my Lindblad equations to introduce a dissipative term, classical like. Yeah. It would be the analogous of the hopping rate in the simple exclusion process. Well, but in order to study the fluctuating hydrodynamics of this model, I have to take the hydrodynamic limit of the quantum Wiener process. And the quantum Wiener process is introduced in this way, and this is quite standard in the open quantum community, where these dBs are the environmental operators. And this can be seen in this Gardiner and Soler. Okay, here we have just considered one dissipated channel, which is the dephasing, in order to, for the sake of simplicity. But the point is that, okay, we have here our deterministic evolution. We add this noise. What about taking the limit of this? And we end up with this fluctuating hydrodynamic equation, which is exactly the same as the one for diffusive systems. Yeah, if you average this, you go back to the Lindblad equation. All right? If you average over these trajectories, you recover the deterministic part, just as you do in the classical case. Yeah, it's an approach. Okay, and then we see what happens. Okay, so, but the point is that doing this diffusive limit, we get the fluctuating hydrodynamics, which is exactly the same, right? With this, and the most important thing is that the mobility here, by cross-graining the noise, we get that the correlation of the noise are proportional to a sigma, which are exactly the same of the classical noise. And the difference, the funny difference, is that for fermions, we get the sigma, the mobility of the simple exclusion process, while for bosons, we get the mobility for the simple inclusion process, right? So this step tells us that in order to study fluctuations of quantum system, large space and time scales, we can apply all the machinery that we have developed for classical systems. And that is what we are going to do. In particular, we are going to say, okay, our fermions are equivalent to the simple exclusion process, to an open simple exclusion process. What can we say in an open simple exclusion process? I would say so, but I repeat, I'm not an expert in open quantum systems, so I'm just trying to see the interplay of the different terms we had in the Lindbladian, and then how can we obtain the fluctuating hydrodynamics and use the classical methods that we know. But, well, we can discuss later. So, what is interesting in the simple exclusion process? We study the statistics now of the total current of the system, the total time-integrated current. And this current was shown by Imparato, Lecomte, and Van Wigland in 2009, that it develops in this limit a non-analyticity that is expressed indeed modulus of S to the third. Okay, and the third derivative of this guy is discontinuous, meaning that we have a third dynamical order phase transition.
H is conjugated to the current?
Yeah, H is conjugated to, yeah, sorry. Yeah. This is H, sorry. This is H cube. So that is the conjugate field to the current. Okay, and this means that we have a dynamical phase transition of third order. We have verified it with the cloning algorithm for the simple exclusion process, all right? And we see that indeed, by taking larger and larger system, we get this discontinuity in the third derivative. Okay, that was predicted already in 2009. But what wasn't predicted was the physics behind it. And that is what I'm going to tell you. What's the physics behind this third order dynamical phase transition at H equal to 0? Okay, let's see if I have an equilibrium set, right? With densities 1/2 and 1/2 at the boundaries. The stationary dynamics for H equal to 0 without doing any bias is given by this. This is a normal trajectory, a diffusive trajectory. If I average this diffusive trajectory, I have the flat profile, 1/2. However, as soon as I bias my system, or I condition my system to have higher currents, okay, different from the stationary one, in this case the stationary would be 0, I have a hyperuniform phase. And this is observed here, right? How this system, despite of having the same average profiles, we see that it's completely different, right? In this case, large wavelength fluctuations are strongly suppressed. This is that here we observe that the same fluctuates. We have bubbles of occupied and empty side. Occupied side are red sides, I didn't say it. And here we have a very hyperuniform structure where particles and holes alternate more than at random, all right? So, and the funny thing is that this kind of transition happens regardless of the values at the boundary. So it happens both in equilibrium and out of equilibrium. And here we see if we plug the system to a reservoir with 0.8 at the left and 0.2 at the right, the stationary dynamics gives me a linear profile, and here is a typical trajectory. And if we bias the system, again, for high currents, we have this hyperuniform phase that again gives me the same 1/2 profile. Okay? So this is quite interesting because in this case, if you observe just to the profile, you wouldn't say to the average profile, if you wouldn't have access to the trajectories, you could not say anything about the difference. But you have to go to single trajectories or, and that is what we're going to do now, study the structural factor, which study the correlation of the density-density correlation function. Okay? So, okay, we studied numerically these profiles. Again, with the cloning algorithm, we have what I told you, that as we bias S, the system goes to the 1/2 profile, and we studied as well the structural factor. And the structural factor, I am studying the classical system. These are, yeah, because of the link with the fluctuating hydrodynamic equation, okay? But as I can use that equation to classical system, now I'm in the classical system setting. And here is the structural factor, right? With the cloning algorithm given by the Fourier transform of the 2-point correlation functions here. But average in the S, well, I should put here, in the H ensemble, all right? And doing this, we have this equation, a very similar one was obtained by Rob Jack and Peter Solich and Thompson. And we see that they are hyperuniform trajectories, characterized that when K is close to 0, it goes linear, okay? And in addition, we don't only have that they are hyperuniform. We also can study the dynamical behavior. And the dynamical behavior is studied through the time-dependent structural factor. And we have here, this is the wavelength K, and as it has exponent equal to 1, the dynamical exponent here is set equal to 1, meaning that in this, for no bias, we have diffusive behavior. But as soon as we bias, we have hyperuniform behavior in terms of spatial structure and ballistic behavior in terms of dynamical behavior. So we go from set equal to 2 to set equal to 1. Good. And what about the current activity fluctuations? Again, there were recent works regarding this joint phase diagram. Here we have hyperuniform phase in the yellow phase. Here we have phase separated. And also in a recent work of Carlos Perez Espigares, we had this similar generalized to the case in which we apply a bulk field through conformal field theory. And they had that this doing a mapping to free fermions when you bias the effective dynamic is mapped into free fermions when you bias S when S goes to infinity. All right. So yeah, they get this dynamical behavior, which is in agreement with the one that we obtained using another approach, fluctuating hydrodynamic approach, and in the phase transition line, they have that a set equal to 3/2, which is a KP set dynamical behavior. Okay, because in the phase transition line, our bias SEP is mapped into a non-biased ASEP. All right, that's the reason why because the ASEP have a dynamical set exponent equal to 3/2. And what we did is study this but we obtained the large deviation function. So we get the 3-dimensional coordinate here, studying the scale cumulative generating function when we bias both the activity and the current. And we have here this phase separation line. We have here the inactive phase, and here we have the active phase. All right, and these are the results. And what about not only the scale cumulative generating function, but also the how are the trajectories in these two phases? Okay. The difference with respect to this case of Rob Jack and Solich in 2015 is that we are considering, recall, the open geometry, right? And here, the phase-separated phase was reached by developing traveling waves. Now, what we have is this. In the active phase, we have hyperuniform behavior, set equal to 1, and in the inactive phase, we have a symmetry-broken phase, where the system chooses either to get fully occupied or fully empty. Okay, and so this is a very nice plot obtained with the cloning algorithm, and it tells you that there is indeed a symmetry-broken phase, and if we average these profiles, we get 0, and if we average this profile, we get 1, except at vanishing boundaries. All right? Okay, and these are the last results in which we take into account the real quantum generator. But in that case, we just can diagonalize up to 11 spins. And we have been lucky. So we have here H equals 0, which is recall that this is the bias of the current. S is the bias of the activity. These are the fluctuating hydrodynamics results with all these, with the local equilibrium approach. But we see here that the system indeed approaches to this value. So things seem that are working in the right direction. And we could as well obtain, obtaining the right and left eigenvectors, we could obtain the structural factor. And here they are. For S equals 0, again, 11 spins, H equals 0.1, and different values of S. S equals 0, and negative values. Negative values meaning that we are in the active phase. Exactly. So this structural factor corresponds to this. We are fixing H equal to 0.1 and studying negative values of the activity. So in the active phase. And we can see some hyperuniform behavior, right? The problem is that with 11 spin, we cannot explore many wavelengths, all right? But this been very nice to compare what the exclusion process gives us on the one hand, and what the real quantum system gives me by performing exact diagonalization. All right. So the summary is that the last deviation function, the analog, well, in an equilibrium system, and its non-analyticities gives me of possible dynamical phase transition present in the system, and that the fluctuation in a family of quantum systems, in this case, given by this tight binding model in the presence of boundary reservoir, dephasing, and if we want to add dissipative hopping, they can be described, the fluctuation can be described by means of the macroscopic fluctuation theory or fluctuating hydrodynamics. And in particular, in the fermionic case, they can feature a dynamical phase transition for atypical currents and also for atypical activities. The hyperuniform phase is characterized with a ballistic behavior. And that's it. Now the question is, okay, what about other quantum systems? What about if we add interactions? And I mean, many questions can arise here. Okay, that's all. Thank you for your time.
Hey. So the Limnad Hamiltonian with dissipation in the bulk, how close is it to the Markov matrix of the SEP? It is mapping between one and the other. I'm guessing the bulk is pretty much the same. Is that correct?
I mean, in this case, the only difference comes from the. I mean, if in this system you take away the coherent hopping and the dephasing, you have the SEP. All right.
Yeah, but if you now take it and do a sort of similarity mapping, can you do that?
I haven't.
To the boundaries.
I haven't done it, but I don't know how how close, but I think, yeah, you.
Okay. So the jump part, where you keep that, right? But is there the dissipation? Is it on the previous slide? Is that a diagonal part to the Hamiltonian?
So the jump operator, which are diagonals, are this one, okay?
Okay, the NK, and they enter the bulk dissipation, and
they act in the defacing, meaning that the defacing leaves the diagonal part untouched. They affect the non-diagonal terms. You see, that's why the quantum coherences disappeared.
Okay.
A long time.
So there's no diagonal part here in the Hamiltonian?
No, I mean, you have this kind of Hamiltonian.
I'm a little confused by your motivation. So, are you interested in the classical CSEP or your quantum system?
So, what I am interested in which is the behavior of the quantum system in the hydrodynamic limit at large space-time scale. Then we have seen that it is at the fluctuating level with these ingredients. It is the same as a diffusive classical system.
Okay,
that is the motivation is to connect ideas and methods of classical non-equilibrium systems to quantum system in the hydrodynamic description.
I understand your motivation, but even when you are only interested in the classical CSEP, you can introduce a quantum analog because exclusion can be mapped onto the fermion. So when you adopt such approach, what is the difference between this quantum analysis?
Yeah. It is different. The other one is just a formal mathematical analog to map in order to study the largest eigenvalue as the ground state of the Hamiltonian. But this is another approach, right? This is not at the formal mathematical analog of these other approximations. But this is taking the quantum system and seeing what happens.
Thank you.
Other questions, Abhishek?
Since it's a quadratic system, I guess in principle you could, in the non-equilibrium state, you could compute 2-point correlations, right? I mean, and then if it's equivalent to the kind of shape, then you expect long-range correlation.
Yeah.
That's something you have checked, or?
Yeah. Because when we measure the structural factor in the quantum system, we actually calculate these 2-point correlation functions.
Okay.
I mean, this structural factor is in the quantum system, right? For the structural factor, you need the correlations of the 2-point density. Yeah, you need this function, which is the.
This is a numerical exact computation.
Yeah. In this case, is the exact diagonalization. All right. In the biased, you could do it in the unbiased one as well. All right.
The questions. Vivier?
Since S and H are conjugated to the total current and activity, this drives the SEP out of the dissipation limits or the dissipative regimes, no? Because then the dynamical exponents are different from 2. So
yeah, you have a plastic behavior.
And can you study the crossover between what happens for small h and s to what happens at larger s and?
I mean, the dynamical behavior is encoded in this. Well, in this, it's been done by Karevsky and Schutz. In all this region, we have z equal to 1. In the vortex, okay, we have this diffusive behavior.
So MFT strictly applies only.
MFT would be assumed around this region, all right, and everything would remain diffusive. Here we are studying the total current, not the spatial average current. So that's why as soon as you go away from the vortex, you have this radical change in the dynamical behavior of the system. Yeah, but in the very large lambda. Well, it's a problem here. These are taking. I mean, the MFT. If you add the corrections to the Lagrangian, if you expand, if you don't take just the optimal profile, you have, in order to have this fluctuating hydrodynamic description, you have to expand the Lagrangian to up to second order. In the fluctuations of around the optimal profiles. Okay. No, but if you consider just and this is important, just the spatial average current, you don't have this any phase transition at s equals 0. All right. For the SEP, the open SEP, without any field and anything, you don't have any phase transition at s equals 0. You have to consider the total currents, and then you have this phase transition into hyperuniform states, but for the total current, not for the.
And in the comparison between the classical and quantum system, can you quantify what remains of the coherence in the quantum system? What remains of the coherence in the quantum system in the large time, or?
We haven't done that. But really nice to be explored.
It disappears, or?
I think it would disappear as soon as you have dephasing. It wipes you out all the coherent terms.
So it's connected to the previous question, because So the local mechanism for dissipation is basically your system is coupled to a Lindblad, and Lindblad is well suited to describe a driven system. So I would expect that the quantum system locally, in a sense that maybe one has to make more precise, does not thermalize. Now you are telling me that if you do the hydrodynamic limit and so on and so forth, that you discover that it satisfies MFT, which implies local fluctuation dissipation theorem. So are you telling me that all the non-equilibrium driving effects are disappearing because of the macroscopic limit?
I think that in that case, the key, again, is the dephasing, because if you don't have the dephasing in the bulk, your system is ballistic, all right? And that was shown by Snidaric. And in that case, I don't know how to unveil a fluctuating hydrodynamic description. But as soon as you put the dephasing, the long time limit leads you to this diffusive-like classical behavior.
Show without the dephasing. Other questions? I think there'll be room for discussions in the afternoon after lunch on this model. If no more questions, then let's thank Carlos again.
Thank you.